This type of actuator can be called an air-to-close, spring-to-open actuator because air pressure moves the stem to close the valve and a spring moves the stem to open the valve. This means that if air pressure to the actuator is lost, the control valve connected to the actuator will fail open, since spring pressure would raise the stem and open the valve. A single-acting diaphragm actuator that's designed to close a valve or fail closed when air pressure is lost looks like this. As you can see, it's very similar to the actuator we just looked at. During operation, air pressure is fed into the lower chamber. This causes the diaphragm to lift, which expands the spring, raises the stem, and opens the valve. When air pressure is reduced, the spring pulls the diaphragm and the stem downward, closing the valve. A control valve using this kind of actuator is said to fail closed because if air pressure is lost, the spring in the actuator will close the valve. A diaphragm actuator with an air line to only the lower chamber is typically an air-to-open, spring-to-close type, which causes a control valve to fail closed. An actuator with an air line to only the upper chamber is typically an air-to-close, spring-to-open type, which causes a control valve to fail open. By controlling the applied pressure, either of these actuators can be used to position a valve anywhere within the limits of travel for the actuator. Regardless of how they operate, single-acting diaphragm actuators are usually represented on process piping diagrams by this symbol. A double-acting diaphragm actuator is called double-acting because air pressure acts on both sides of a flexible diaphragm to position a valve. A double-acting diaphragm actuator consists of a casing, a flexible diaphragm, an upper air supply port, a lower air supply port, a stem, and a valve position indicator, which shows the position of the valve. The center of the diaphragm is supported by metal plates, and the outer edge is sandwiched between the rims of the upper and lower halves of the casing to form an airtight seal. This arrangement divides the casing into two chambers, an upper chamber and a lower chamber. The upper end of the actuator stem is connected to the metal plates and the diaphragm, and the lower end is connected to the valve stem. When air pressure is applied to the upper chamber, the diaphragm and the actuator stem are pushed downward, and the valve closes. Air in the lower chamber is exhausted through the lower air supply port. When air pressure is applied to the lower chamber, the diaphragm and the stem are pushed upward, and the valve opens. Air in the upper chamber is exhausted through the upper air supply port. These actions make stem movement and therefore valve position proportional to the difference between the two air pressures applied to the chambers of the actuator. Controlling the applied pressures enables the actuator to position the valve anywhere within the limits of travel for the actuator. In most applications, accurate positioning is achieved by using a device such as a positioner to add air to one side of the diaphragm and bleed it off the other side. On a piping system diagram, a double-acting diaphragm actuator may be represented by this symbol. However, it may also be represented by the same symbol used to represent a single-acting diaphragm actuator. Some valves require relatively long stem travel or a large amount of force to be positioned. In these situations, a piston actuator is probably more suitable than other types of actuators. This is one type of piston actuator. It's called a single-acting piston actuator because a controller or similar device controls the air pressure on one side of a piston. When air is fed through this air supply port, the piston moves along in a cylinder, compressing a spring and opening the valve. Air on the other side of the piston leaves the cylinder through an air vent. When air pressure is reduced, the spring expands, moving the piston in the opposite direction, closing the valve. If air pressure drops below a predetermined value or is lost completely, the spring will force the piston down to close the valve. In other words, the valve will fail closed. Since air pressure is only fed to one side of the piston, this type of actuator is called single-acting. However, there are piston actuators that have air pressure supplied to both sides of the piston. This type of actuator is called double-acting. The parts of a double-acting piston actuator are similar to those of the single-acting actuator. However, this one doesn't have a spring, and there's an air supply port on each end of the cylinder. When air pressure is fed into this supply port, it pushes against one side of the piston, which moves the piston to open the valve. Air on the other side of the piston is bled off through the other air supply port. When air is fed in through the supply port in the opposite end, the piston is pushed in the other direction, closing the valve. Air is bled off through the other supply port. Filling the cylinder with air and bleeding air from the cylinder can be controlled by a device called a positioner. On a piping system diagram, single-acting and double-acting piston actuators may be represented by this symbol. However, a double-acting piston actuator may also be represented by this symbol. A vane actuator uses air pressure acting against a paddle or vane to position a valve. In general, a vane actuator is simple in design and relatively small for the amount of force it can supply to open or close a valve. Vane actuators are used primarily with rotary-type valves, such as ball, plug, and butterfly valves, because the vane rotates the valve disc. Here's a cutaway of a vane actuator that operates a butterfly valve. When air pressure is supplied through this air supply port of the vane actuator, it pushes against a vane, causing the vane to swing across a housing. This turns a shaft. As the shaft turns, it opens the valve. Air on the other side of the vane is bled off through another air supply port. When air pressure is supplied to the opposite supply port, the vane is moved in the opposite direction, closing the valve. Air on the other side of the vane leaves through the other supply port. Vane actuators, like other actuators, can be spring-loaded or set up with other devices so that a valve will fail in a safe position. On a piping system diagram, a vane actuator can be represented by this symbol. Pneumatic actuators are commonly operated by air signals that come from a controller. In some cases, the controller signal alone isn't enough to overcome forces on the actuator, such as friction in the actuator or the valve stem, or fluid pressure acting against the valve disc. To overcome these forces, some actuators must be provided with a different supply of air that's capable of applying higher pressures than the air signals from the controller. This is accomplished by using a positioner along with the actuator. Basically, a positioner is a device that uses a separate supply of air to ensure that an actuator correctly positions a valve in response to a change in the air signal from a controller. In other words, a positioner's job is to place the control valve in the position called for by the controller. The positioner shown here has 3 gauges. One gauge indicates the supply air pressure to the positioner, and another indicates the output air pressure to the actuator. The third gauge indicates the input signal pressure from the controller. A mechanical linkage joins the actuator stem to the positioner. This mechanical linkage may also be called a feedback linkage. As the actuator stem moves up or down, it also moves the linkage. The position of the linkage indicates to the positioner when enough movement has occurred to correspond with the air signal from the controller. When a positioner is used with an actuator, the signal from the controller goes to the positioner instead of directly to the actuator. The positioner controls the source of air that enters here and is sent to the actuator through this line. When the controller sends a signal to close the valve, the positioner receives the signal and converts it to the appropriate air pressure using this air supply. This pressure is then applied to the actuator to close the valve. The feedback linkage indicates to the positioner how far the valve is from the desired position, in this case, fully closed. As the valve moves toward the fully closed position, the feedback linkage causes the positioner to change the air signal to the actuator, so that as the valve reaches the fully closed position, actuator movement is stopped. On a piping system diagram, a positioner may be represented by this symbol. Actuators, like other process components, are susceptible to mechanical problems. Since an actuator problem can adversely affect the operation of a process, it's important to know how to identify actuator problems when they occur. The following discussion is not intended to enable you to isolate the exact cause of an actuator or control valve failure, but it can be used to help you narrow down the scope of a problem to minimize the effect it has on a process. Often, an operator can detect an actuator problem by looking at its valve position indicator and comparing it to the position called for by the controller. For example, If the position indicator is showing that the valve is closed, but the flow indicator on the controller is showing that the flow is still continuing through the valve, then the valve seat and disc are probably warm, allowing leakage through the valve. However, if the position indicator shows that the valve is open when it should be closed, the problem could be in some other part of the control valve or in the actuator. For example, a diaphragm actuator will not be able to properly position its control valve if its diaphragm ruptures or if air pressure to the actuator is lost. Loss of air pressure could result from leaks in the actuator around the diaphragm edge, from leaks in the air lines to the actuator, or from a crimp that blocks the flow of air in an air line going to the actuator. If a positioner is used on an actuator, its gauges should be checked to make sure they have the appropriate air pressure readings. Sometimes problems with a positioner can also result from a loose or broken feedback linkage, so it should be checked too. Regardless of the reason for the failure of an actuator or a control valve, there are some basic steps that can be taken to minimize the effect that the failure has on the process. Some actuators have manual operators on them that may be used to regain control of the process flow in the event of an actuator failure, while other actuators and control valves may have manual bypass lines around the failed components. Bypass lines can usually be placed in service by isolating the failed actuator's control valve and positioning the bypass valve to restore flow. When either a manual operator on an actuator or a bypass line around an actuator is used, it will probably be necessary to maintain communications with the control room to ensure that the proper flow rates are maintained in the process. Since there's so many different possible configurations that actuators and control valves can be arranged in, you should check your company's procedures before operating any actuator manually or on the bypass. A typical single-acting diaphragm actuator consists of a casing, a diaphragm, an air supply port, an air vent, a spring, a stem, and a valve position indicator. The indicator shows the position of the valve. A double-acting diaphragm actuator consists of a casing, a flexible diaphragm, an upper air supply port, a lower air supply port, a stem, and a valve position indicator, which shows the position of the valve. This is one type of piston actuator. It's called a single-acting piston actuator because a controller or similar device controls the air pressure on one side of a piston. When air is fed through this air supply port, the piston moves along in a cylinder, compressing a spring